All right, welcome everyone and hello. We are in week 3 heading into Monday's class. This is my 12.5B pre-class video. Don't have so much on the administrative side. Sent out an email this morning just with kind of the week 3 stuff. More or less, we're getting down to the grind here. Kind of attend class, recitation, do your homework. We have another quiz on Thursday, all that good stuff. But yeah, kind of more or less the same as last week. I guess the one thing that is noteworthy this week is that we have a class Monday, Wednesday, and Friday. We've missed a couple Mondays here just with Labor Day and the semester starting on Wednesday and all that sort of stuff. So this is going to be kind of our first full week. But other than that, yeah, nothing super special about this week. I thought for this video, it might be fun for me to do a particular problem and talk a little bit about why one of the formulas is the way it is. And so my goal is to do this problem right here, find the distance between this point, 1, 2, 3, and this plane x plus y equals 0. So I've chosen, you know, relatively nice values for my point and my plane and all that sort of stuff. And you may have already come across this problem in web work. There's a couple that are like this. And so I thought it might be fun to do this and just kind of explore a few sides of this that you may not have originally thought of. And so again, the statement of this problem is a little bit vague, right? Whenever it says find the distance between a point and a plane, what it really means is the shortest distance, right? We want to go in this optimal distance here that goes somehow straight to the plane, and whatever that shortest distance is, that's what we call the distance between the point and the plane. But of course, right, if you kind of take any old point anywhere, right, this distance may be longer and this distance may be longer still, right? And so that's why it's a little bit vague, and so you just have to understand exactly what it's asking. So we're trying to find this length right here, the shortest distance between the point and the plane. And of course, right, this is going to be kind of in this direction that goes straight to this point. Right, so I mean, one initial thought is if we could figure out this point right here, the point that's somehow directly below kind of the point that we're interested in, the 1, 2, 3 in our case here, if we could somehow figure this point out, then we could go ahead and just find the distance between points. We come up with an equation from that, from 12.1, and that would be one way to solve this problem. Unfortunately, this kind of takes some work to figure out what this point would be, and maybe it's not completely obvious, right? Maybe some of the things that you would guess aren't exactly correct. And so what we're going to do here is that we're going to actually use vector projections, right? And so you may remember from the web work, if you've seen this problem already, if you haven't, it's coming up soon, right? That the distance between this point, and so I'm going to go ahead and call this P here, and this plane is going to be given by the absolute value of PR dot n divided by the magnitude of n, where n is this normal vector. So n is normal vector to the plane. And we have our P, and so the only question is, what is R, right? And R is any point on the plane. And this should look quite familiar. This is actually very close to the definition of the scalar projection. So we denoted with this comp, right? The scalar projection of PR onto n, right? So let's just kind of do a quick review. We probably had something like this for our original definition, the scalar projection of A onto B, or something like this. And this was just A dot B divided by the magnitude of B. And so we can see that this is very close to this. The only thing is that for a distance, we want to make sure that this is positive. And so certainly the denominator is positive. We want this numerator, this dot product, to be positive here. And so really it's just the absolute value of the scalar projection here. And so again, applying this here, the absolute value of P R dot n onto n here. So this right here is just the scalar projection of PR onto n. And so I want to talk a little bit about why this would be the case, right? So we're going to go out and we're going to find some point R, right? And it's very probable that R is not directly underneath this P like we'd like it to be here. So maybe R is over here or something like this. And again, this is our P. Now, if we find PR, that's going to be this vector right here. We want the piece of that vector that just goes straight down into the plane, right? And well, one way to do this, right, is if you have some normal vector. This is some normal vector. This is kind of, remember, normal vectors are at this 90-degree angle. I'll just go ahead and do a couple 90-degree angles here. Just remember, normal vectors are at, this 90-degree angle. They're orthogonal, or they're normal to the plane. So we want the piece of PR that's going in this direction, that's going straight to the plane, right? And so that's basically going to be this blue line here. But we want to make sure that that we get the positive length of this thing. So that's why we're just going to apply some absolute values here. So that's why this formula works. And so again, if you don't want to remember this, right, it's not really a separate formula. Like it's maybe come up in web work. Maybe it feels like it's just something completely new and separate. In reality, it's something that you saw back in 12.3. So it's not new at all. We're just going to be finding this scalar projection of PR onto n, right? And we want to make sure that this is some positive number. So let's go ahead. I'm going to go ahead and delete these. But again, this is where it comes from. And now I'm going to go ahead and solve the problem. So I'm going to go say this is the solution to the problem here. And so again, we already know what P is. P is 1, 2, 3. We can figure out what our normal vector is. So our normal vector, remember for any equation of a plane, we have maybe AX plus BY plus CZ is equal to D. The normal vector is given by these coefficients, A, B, C. So in this case, right, with our equation of the plane, we can write 1x plus 1y plus 0z is equal to 0. So we can figure out what our specific values are for A, B, C, and D, right? So this is our equation of the plane, x plus y equals 0. And now we can see that the normal vector in this case is going to be 1, 1, 0. So our normal vector is going to be 1, 1, 0. And then the last thing that we need in order to apply this formula is that we need some R value, some point that's on the plane. And so there's lots of points that are on this plane, right? There's infinitely many points that are on this plane. They're all over the place here. And what's amazing is that you can choose any of them, that it doesn't matter what R that you choose. And this formula works just as well. And so let's go ahead and let's try maybe the easiest one to start off with. I think the easiest point is 0, 0, 0, right? So let's go ahead and do 0, 0, 0. 0, 0, 0 is on the plane, right? When I go ahead and I plug in 0 for x and 0 for y, does 0 plus 0 equal 0? Absolutely. And so this is a fine point on the plane. And then maybe if we have time, if I don't feel like this is getting too extremely long, then we could go ahead and choose like another point that's on this plane. So for instance, we could do 1 plus -1 is equal to 0. So we could have the point 1, -1, and z can really be anything. Let's just keep it as 0. So we'll just say that this is some bonus problem here. So if we have time, if not, try it out on your own and see that you actually get the same distance. So this formula is wonderful because it works for any point on the plane, any R value on the plane. And so that's kind of rather remarkable, I would say. All right, so now let's go ahead and calculate out PR. So whenever I calculate out a vector PR, again, I'm thinking I'm starting at P, I'm ending at R, and I just ask myself, how many steps did I take? So I start at 1, I end at 0, I must have taken 1 step backwards. I start at 2, I end at 0, I must have taken 2 steps backwards. I start at 3, I end at 0, I must have taken 3 steps backwards. So this is just my way that I figure out, vectors like this. So I start at P, I end at R, and I ask myself, how many steps did I take? All right, now we have all the pieces. Now we just need to assemble them. So this distance is going to be equal to, we have, let's see, PR, -1, -2, -3. We're going to dot product that with 1, 1, 0. and we're going to divide by the magnitude of n, which is magnitude of 1, 1, 0. And so let's go ahead. Oops, I forgot my absolute values up here. So when I apply this dot product, I get -1 plus -2 plus 0. So that's just, okay, I guess -3 altogether. And you can see that this is why you want those absolute values, right? Because a negative distance doesn't really make a whole lot of sense in this context. And so that's why these absolute values are here. So this is going to end up being 3. But let's not forget about our denominator, right? So our denominator here, we need to take the magnitude of this vector. So this is going to be the square root of 1 squared plus 1 squared plus 0 squared. So this is just going to be the square root of 2. And so this right here would be my final answer. This is the distance between the point and the plane. That wasn't too horribly long. Let's go ahead and I'm going to do this other problem here, where I choose this different R value. And let's hope that we get the same number at the end of the day. So again, we need to recalculate our PR, right? Our N's going to be the same, 1, 1, 0. But we need to recalculate our PR. So again, we're thinking we're starting at P, we're ending at R. How many steps did we take? So I start at 1, I end at 1, I took 0 steps. I start at 2, I end at -1. That means I must have taken -3 steps. And then finally, I start at 3, I end at 0, I must have taken -3 steps. So you can see now we get a different vector. Before we had this vector up here, now we have this vector. And amazingly enough, it will not matter. So let's go ahead and calculate this out and verify. So our distance is going to be equal to, and again, we're going to take the absolute value of the dot product between PR and our N. Oops. And then we're going to divide that by the magnitude of N. And so when we take this dot product, we get 0 times 1 is going to be 0. We get -3 times 1, that's going to be -3. And we get -3 times 0, that's again going to be 0. We put it inside of absolute values. And so you can see, again, we get 3 on top. And of course, the magnitude of this normal vector is still going to be this root 2. And so you can see, even if you choose a different R value, and that's again kind of the amazing thing about this formula, is that it works no matter what point on the plane that you choose. Of course, it does have to be on the plane. If you choose something that's not on the plane, right, it's going to give you some different distance. But if you choose any point R on the plane, this formula works. And so I think that's a rather remarkable and wonderful thing. So anyway, so I hope that helped you out understand some of these distance problems. In particular, this time I went over the distance between a point and a plane. There's a very similar storyline or argument that you can make between a point and a line. And then, of course, you can kind of upgrade these to a couple of planes or a line and a plane, all that sort of stuff. So yeah, I hope you guys enjoyed. I will talk to you later.